Okay, this video is looking at distances on Earth. It's the second video in the series, and we're looking at small circles. So we've already identified the difference between great circles and small circles, and now we're just going to be looking at calculating distances between 2 points on small circles. A little bit more difficult than great circles. So when we look at the points on the same small circle, if you remember your small circles are these little ones here, the ones that are north and south of the equator. So the equator itself is a great circle down here, and hence we have this as the radius, whereas those small circles, we're going to have a radius that's going to be shorter than a great circle radius. Because great circles are all the same size, we have that radius that is the same for all of them. Small circles, however, we are going to have to actually calculate the radius of the circle first before then finding that arc distance along the circumference between the 2 points. So basically, points on the same line of latitude, that's our small circles, they lie on the circumference of the small circle. We're going to find the distance between the 2 points by calculating the length of the arc of the smaller circle. And as I said, to do that, we need to find the radius first. And so really that's what we're going to do. So if we have a look first, we've got, just at this picture here. So I've got the Earth, I've got a point up here on a small circle that is 40 degrees north. So you can see north of the equator on that small circle, it is 40 degrees north. Now that would be our latitude. What we need to look at is taking this three-dimensional section and putting it out into a flat one. So basically we want to know this radius. So that's from the centre to the edge of this small circle. So we want to find little r, okay? Big R is going to be the radius of the great circle at the equator. Little r will be the radius of the small circle. So if we draw first our radius of 6,371 of a great circle, that's the equator, and then our point is 40 degrees north. Okay, that gives us our little wedge here. Now, if we then go directly up and out, we get our 90-degree angle. This line here is the radius of our small circle up here. Now the Z rule, if this is a parallel line, that Z rule means that this angle and this angle are both 40 degrees. We know that this distance is 6,371, and we just need to find this distance. Now, in order to do that, we actually use cosine. So if we know our angle is 40 degrees, and when we have, I'm not sure if you actually remember this, but if you have an angle here, then this is the opposite, because it's opposite the angle. This one is going to be adjacent, and this one is going to be the hypotenuse. So this one's the hypotenuse, because it's along the side of the right angle triangle, and this one is adjacent, or next to the angle. So using that, SOHCAHTOA, so SOHCAHTOA, cos is adjacent over hypotenuse. So the cosine, and that will allow us to find the adjacent, is going to be adjacent over hypotenuse. So the cosine of 40 degrees, which is what our unknown theta is going to be, the adjacent is our little r. So if we look over here, adjacent is little r, and h for hypotenuse is going to be the 6,300 big R. our 6,371 kilometres, the radius of the Great Circle at the equator. So what we want to do is just rearrange for r. So if we rearrange, we end up with the radius of the small circle equaling the 6,371 multiplied by the cosine of 40. And that will basically give us, technically it should be wiggly one, an approximation, we've rounded it, 4,880 kilometres. And so that gives us our parallel of latitude being the radius of that parallel. So 40 degrees north, the parallel, this one, parallel to the equator, that is at 40 degrees north of the equator, that runs through that point, has a radius of 4,880 kilometres. Now that we know that, you know that radius, you can work out the distance around the Earth at that latitude and speed of rotation of a point on the Earth at that latitude. Okay, so what we can do is basically write down the rule for circumference. Oh, wrong one, pen. So circumference is going to be 2 pi r. And so that's going to be 2 times pi times 4,880 kilometres. Okay, and that's going to equal 30,662 kilometres. Now, that means we know the circumference of that parallel. Now, if we were to put these two together, these two formulas, what we end up with is our circumference of 2 pi r. Actually, we shouldn't write circumference. What we're after is our distance. So basically, distance is going to be, let's start with our circumference measurement, so 2 pi r, except that the r part is a radius of the parallel of latitude. So it's actually going to be like this, radius of the parallel of latitude, and to find that we used big R, which is the radius of the equator, 6,371, multiplied by the cosine of the angle. So, if we have a look at, when we compare to a great circle, the distances are reduced by the factor of cosine to theta, the cosine of theta, so whatever that theta is. So if we're going to reduce it that way, what we can end up with is basically, if 1 degree is approximately equal to 111.2 reduced by the cosine of theta, where theta is the angle of latitude. I can't actually fit latitude in. Okay, there we go, angle of latitude. And we know that because over here, this is the angle of latitude. So from the equator measured north, latitude is a north or south measurement. It was 40 degrees north. Okay, and so your 1 degree is equal to 111.2. That comes from this part here. So knowing that this distance and that general circle that we worked out with great circles, we worked out that 1 degree in a great circle is equal to 111.2 approximately. And because of this working that we've done here, we can see that the distance on a small circle is reduced by the factor of the cosine of the angle of latitude. So this means basically that on a parallel of latitude or a small circle, 1 degree, that's a degree, is equal to 111.2 multiplied by cosine of theta, where theta is equal to the degree, that's not really working for me, degree of latitude I've got too many T's in there. It's actually one T. L-A-T-I-T-D. And distance basically, to find the distance, what we need to do is do the angular distance multiplied by 111.2 multiplied by the cosine of theta. Now you need to remember that that angular distance is actually difference in longitude. Oh, that didn't spell that one right, did I? Now, do remember that your latitude is your north-south, longitude, east-west, east-west. All right, so let's have a look at an example. So, we're going to find the distance to the nearest kilometre between two places whose positions are 25 degrees north, 110 degrees west is the first position. The second place is 25 degrees north and 15 degrees east, respectively, again, in that order. So what we're going to have a look at is distance for 1 degree. For 1 degree. I should actually probably write distance for 1 degree is going to equal our 112, wow, I'm really having a time of it, 111.2 multiplied by the cosine of theta. Now, I know I put the sort of the distance part before this is the equal, but this is just for 1 degree is equal. And then we use our longitudinal difference to work out angular distance in order to multiply it for the total distance. So if we do distance for 1 degree, and then we just sub in. So 111.2 times the cosine of, and if you see here, they are both 25 degrees north, and that's because they're on a small circle, so they both have the same latitude. So this will be the cosine of 25 degrees. And what we end up with, actually, let's keep this as accurate as we can. So we know that's what we need to do here. So then down here, our angular distance is going to equal longitude 2 minus longitude 1. Now, the only problem with this, now that I've done it, is if we have a look over here, we've got 110 west, 15 degrees east. Now, if you remember what we said in the Great Circles video, these are on different sides. So west and east on different sides, and therefore we're going to add them. So that's going to be added 15 degrees and 110 degrees, which will give us 125 degrees. Now we can actually work out distance, and that's going to be equal to angular distance multiplied by 111.2 times cosine of theta. Now we know our angular distance is 125, 111.2 times cosine of 25 degrees, which we have up there. And when we calculate all of that together, we get 12,597.68 kilometres. Now it does say that we need to round to the nearest kilometre, and therefore the distance between, that was supposed to be a 1t, the 2 points is 12,590, I see it's 0.68, and so that means I'm going to round it up to 98, 12,598 kilometres. Now, a quick criteria check. So up here, technically, this part we didn't have to worry about, but writing that tells us that we know that part of this needs to go in here. But as long as we have this formula, so this one is a formula, K1, M1, and then this one here is just subbing in K2. Now, we didn't actually calculate anything in that one, so no K3. This one is a K1, M1, this one is a K2, this one is K3 where we calculated. This is K1, definitely a formula, and M1 as well. K2 where we've subbed in, K3 for calculating C1 for units of measure, M3 down here for our concluding sentence. And again, we get our C1 for including units down the bottom. Now let's have a look at a slightly different one where we're looking at the shortest distance. Okay, so for this question, we're finding the shortest distance to the nearest kilometre between two places at positions 40 degrees north, 170 degrees west, and 40 degrees north, 26 degrees east. So you can see, because they're both 40 degrees north, they're both on the same small circle or line of latitude. And because we're working with latitude, our angular distance is going to include the difference for longitude. Whereas when we're looking at great circles, we find the difference between latitude when we're working with longitude. So, the first thing we're going to do is look at longitudinal distance. So, angular distance is going to equal longitudinal 2, take longitudinal 1. Now we're going to have a look, and we'll say, okay, when we have a look at that, we've got 170 degrees west, 26 degrees east. Now, they're different. So just like when we looked at latitude, and if they were both north or both south on the same side of the equator, if these are on the same side of the prime meridian, then we can subtract them. But when they're on different sides, we're going to add them. And so to do that, I'll just make that a plus because they're different. And so that's going to be 26 degrees and 170 degrees. Now if we add those together, we get 196. Now here's the thing, the shortest distance is actually not the shortest angular distance, shortest angular distance is not going to equal 196. Now here's why. Once you hit the halfway point, so if you've got a 360-degree circle, so here's our circle, once you go 180 degrees, you're halfway. So if I start at this point, I go 180 degrees, I'm half the way around. But if I go more than 180, then I've actually made this much of a circle, and the distance from this point all the way around is more than the distance from here to here. So if I go from here all the way around, that's longer than here to here. So because my answer is 196, I know I've gone more than halfway. Therefore, my shortest distance is actually going to be the 360. I'm going to take the 196, and then that's going to tell me that my shortest angular distance is actually 164 degrees. So that's the side that between the 2 points on that circle that is shortest. So now I have my shortest angular distance. I'm going to say that my distance is equal to angular distance multiplied by, 112, no, I don't know why I keep wanting to write 112, 111.2 multiplied by the cosine of theta. Now I just sub in, so my angular distance, my shortest one, is 164 multiplied by 111.2 multiplied by the cosine of, and our degrees, if we have a look back up here, so this is our lat, the one that's the same, 40 degrees. Okay, and then once I calculate that, I basically get 13,970.2 kilometres. And it's asked me to round to the nearest kilometre, therefore distance, oh actually sorry, it's the shortest distance between points is 13,970 kilometres. So 0.2 means I just keep it the same. So let's have a look. So we've got a K1M1 here, I've got a K2 and a K3 to calculate. Over here I'm just subbing and calculating, so no rule, but I have subbed in. Over here is my K1M1 and my rule, my strategy, this is how I'm working it out. Then I've subbed in for K2, I've calculated here, I've written units here, I've got M3, my concluding sentence related back to the question, and units again. So I've hit all of my criteria along the way. Okay, so what's really important now is that you complete the worksheet, small circles, distances on small circles worksheet. You would have done distances on great circles worksheet last time. Once you've completed both of those worksheets, you can move on to exercise 6.2 from the textbook pages. That will give you some practice on both types of circles, not just practice on both of them, but because it's mixed within the question set, you will have to actually identify which type of circle you're working with from the information you're given in the question. So remember, what you're looking for to know whether it's a great circle or small circle is the coordinate that is the same. So if it is the first one, the north or south, then you're dealing with a small circle. Small circles are measured north or south of the equator, and so if they are the same, they are on the same small circle. If the longitude is the same, or the second coordinate, it means that they are on the same meridian. So they're on the same great circle, and you're looking at just calculating the distance on that great circle.